Okay, welcome. Let us continue with our lecture on linear vector spaces, and this is eighth part of lecture on course PH3103 at IISER Kolkata. So today we'll start with the new notation which was introduced by the Dirac for representing the vectors and dual vectors. Paul Adrien Morrison Dirac came up with the interesting notation called bra and ket notation. It comes from the word bracket, which is broken into bra and ket. So here all vectors are represented by a ket, or symbolically it is written like this. For example, vector A is written like this. In our matrix notation, we have written vector A with its component as a column vector. So it's the same notation, but which is written as what we call a ket. Here, the dual vectors are denoted by what is called bra, or it is exactly reverse to do the ket given by the symbol. And here inside you can give the name of your dual vector, as we have done in the case of vector itself. For example, in our case, a dual vector called A, which we call A star, which becomes cumbersome at some stage, which we can write in the ket notation like this, which becomes a dual vector. But in the case of our vector notation as a matrices, we have used it as a transpose of a column vector that is a row vector. We represent a dual vector as a row vector so that their dot product becomes a number, and here the scalar product is an operation between the bra and ket, or the vector and dual vector. In our vector notation, it is a vector A dot B. In our matrix notation, it is A transpose B, and in our bracket notation, it is bra A B ket, which gives you a simple number, and that is a dot product between these two vectors. This has become an extremely powerful and useful notation, especially in the quantum mechanics. So physicists seems to have able to come up with the interesting notation by which the entire calculation become more transparent. In the case of a complex vector field, this number alpha is complex, and in the case of quantum mechanics, it is always complex vector spaces which are used, but we can use. Idea is very similar, it is not too different. Let's continue and express some of the things which we have already expressed in our older notation in terms of Dirac notation. A vector can be expressed in terms of basis element. This is ket V, that is a vector V is written in terms of the basis element. So this is a vector basis, so it is written as a ket, and these are the component of vector. So it's very similar to this. We have a dot product between the basis vector, which is in terms of bracket notation, the dot product between the vector basis and the dual basis is equal to delta ij, which is orthonormal to each other. We can transform a basis into another basis. This is a vector or ket for the basis vector E. It is a vector basis, and then this is a transformation matrix, and this is a new vector basis which is represented by ket. Again, we can do this for dual vectors. It just gets flipped around, and then B also can be get transposed as I have seen. Now we can see about the dot product, or what happens to the dot product under the transformation. So we have transformed this and taken the dot product using this is a dot product in the new basis. This is a old basis, and this is the transformation metric, and we clearly see that when a transpose A becomes delta Ij, norm is preserved, or they are called orthogonal vector. Again, we can go into vector representation itself without going into basis, where the vector is represented by V, and the transformation and the new vector or the new component. There is no new vector, it is the same vector represented in two different bases. The new component are given by V bar inside the ket notation. So these are some of the translation of what we have done into bracket notation, so that if it is not already introduced in the quantum mechanics, you can put things in the proper context. Let's look at the example for vector transformation. This is where some of the confusion comes about. I hope you will recognize this. I am leaving it in a bit hazy manner itself to create the confusion, and then we can have a discussion sometime over this. Let's the transformation matrix in R2. Let's consider the transformation matrix is given in terms of an angle cos theta sin theta minus sin theta cos theta. The transformation matrix is a rotation of a vector by an angle theta. Now we see that the component of vector V after transformation can be given by the component u1 and u2. This is simply operating our matrix or multiplying our matrix on the column vector v1 and v2, and then we obtain this expression for u1 as v1 cos theta plus v2 sin theta, and u2 as a minus v1 sin theta plus v2 cos theta. Tan of the angle with respect to x-axis by the vector v is given by v2 by v1, and the tan of the vector u is given by u2 by u1. Now in fact we see that the vector u is not anything new. It is just that it is transformed vector or rotated vector by an angle of theta using this transformation. So you see that our basis and our vector v in terms of component v and u, and then we see that there is a vector u with the component u1 and u2, and the theta is angle between them, and theta is a angle, that is a rotation operation which we have done. Now it looks like it is in the same basis. In principle, we have kept the vector same, but rotated the basis, which results in the changing in the component. So there are actually two kind of a transformation. One is called the active transformation and the passive transformation. In the active transformation, basis itself transformed, and the vector itself changes. In the passive transformation, you see the vector remains same and the component get changed. So of course I don't want to go very detailed into that. You have to first realize there is a confusion in that, and then we can sit and discuss about to show that there are these differences, and during some time in between in the course we can discuss this active and passive transformation with little more careful or little more insight when we go along. Let's leave it behind and proceed with another most important concept in the linear vector space, that is or even in the matrix algebra, because matrix usually represent a set of all linear transformation from one basis to another basis, so these two are closely related. A diagonal matrix only scales the basis vector. So it would be interesting to have such a transformation. What they do is that the scale individual component and become a new one along the only diagonal. So basis vector gets scaled, but in general all the components get changed, and sometimes it is good to have realize a transformation as a diagonal matrix only. But before getting into that, we have to try to see and understand what the eigenvalues and eigenvectors represent. Now, when you are given a vector transformation, that is a linear transformation on a vector, is it possible to have a vector which does not change with that vector, with that transformation? That means you go around merry-go-round, but in the center point, it doesn't change. It remains same because the center of the rotating system is remaining rest. So under your rotation, the center remains the same, and that is what we call does not. Or there are more serious example which we will come back later. So more generally, we can say that is there a vector which simply get scaled by a factor lambda, the direction does not change, only magnitude gets scaled. The formally such a thing is called the eigenvalue problem, where you have a vector V transform under a matrix operation, or resulting in a same vector which is scaled by a eigenvalue. So this is called the eigenvalue problem in the matrix. So the vector V in such is called the eigenvector of the matrix or operator A, and the lambda is called the eigenvalue of the operator. So it is a combination eigenvector and eigenvalue which depends on the property of the transformation A, and it can be determined, the both eigenvector and eigenvalue can be determined from the equation, eigenvalue equation. The procedure goes as follows. First, we need to determine the lambda eigenvalues. Once we obtain the eigenvalues, we substitute back in the equation, this equation, and obtain the eigenvectors too. So that is a general procedure. To solve for the eigenvalue, what we need to solve is a called characteristic equation, which is given as a minus lambda into identity matrix. So when we set this equation to 0, we get a polynomial equation in lambda, and then we solve this polynomial equation. In the case of n dimension, we get nth order polynomial for the characteristic equation, and we have n eigenvectors in general. Some of them could be same. That case we can let's take an example and see how we can solve this eigenvalue problem systematically. Let's take the simplest matrix in 2 dimension. A is equal to 0, 1, minus 2, and minus 3. So first we have to solve the characteristic equation, that is matrix A minus lambda into identity matrix. After a trivial simplification, you get this condition. We set the determinant of this to 0 to get the characteristic equation. Since it is a 2-dimensional space, we get a quadratic equation for lambda, and we get 2 eigenvalues, and we know exactly how to solve the quadratic equation, and we have the values of eigenvalues. Lambda 1 is equal to minus 1, uh, and lambda 2 is equal to minus 2. It is trivial to solve this. Now all the eigenvector corresponding to the eigenvalues lambda 1 and lambda 2. Let's say that V is an eigenvector corresponding to eigenvalue lambda minus 1, and the U is the eigenvector corresponding to lambda is equal to minus 2. So we substitute this in the characteristic equation or eigenvalue equation and write down explicitly in terms of lambda. So the characteristic eigenvalue equation is A minus lambda 1 into V. We can write it explicitly in terms of matrix notation as minus lambda 1, 1 minus 2, minus 3 minus lambda 1. This is multiplied with the column vector V1 and V2 and set to 0. So we get two equation in this case because lambda 1 is a minus 1. We get simplify this equation, and we get V1 plus V2 is equal to 0. Both the component give the same values, and what we have is a constraint V1 is equal to minus V2. So in general, the eigenvector V corresponding to eigenvalue lambda 1 can be written as a alpha into minus 1 minus 1. Based on this solution of characteristic equation, it is not possible to determine the value of alpha, and alpha remain an arbitrary number. Let's go ahead and solve for the second eigen vector, which is U corresponding to the eigenvalue minus 2. We explicitly substitute for the vector equation, and then we obtain the corresponding equation for the lambda is equal to minus 2 is 2, 1, minus 1 and minus 1 multiplied by u1, u2 equal to 0. Again, interestingly, we find that both equation corresponding to the same constraint, that is 2u1 plus u2 equal to 0, implying that u2, sorry, there is a mistake here. This should be u2 equal to minus u1. Okay, and then we obtain the vector component can be in general written as u as a beta into 1 minus 2. But it should again see that based on the constraint, the beta cannot be determined and it remains arbitrary number so far. Now we have solved for the eigenvector V is equal to alpha into 1 minus 1 and U is equal to beta into minus 1 and minus 1 and minus 2. So we don't have any condition for alpha and beta, so it is left to our choice. We can choose whatever number we want to. We may simply choose alpha to be 1 and beta to be 1. But one of the useful way to choose beta is to normalize the eigenvector. We can choose alpha and beta such that hence obtain the eigenvectors are unit vector. That choice of finding out beta leaves us with the alpha is equal to 1 over square root of 2 and beta is equal to 1 over square root of 5, and the resulting vector is v is equal to 1 over square root of 2, 1 minus 1, and u is equal to 1 over square root of 5, 1 minus 1. We can check that whether these vectors are orthogonal to each other or not, and so on. For example, there is with the red note comes is an homework. This is a homework you need to submit along with the notes for this video. Here you need to find the eigenvalue and eigenvector for the matrix A is equal to 2, 332. This is a symmetric matrix. Some interesting result concerning that, which we will highlight little later. Of course, to make your life difficult, I could have given 3 into 3 matrix. I would say it is a sheer waste of human power. Sorry for this mistake. Um, so it is a waste of human power. You can simply go to a computer and ask, give a large matrix and find out the eigen value, solve the eigenvalue problem. You get, whenever you get time, you could check with the Mathematica and see how it is giving results. It usually gives a normalized eigenvalues. Let's get to another important concept in the uh, linear transformation, and of course linear transformation means also the vector space, and now we have seen the eigenvalue. Let A be the matrix with the eigenvalue lambda and eigenvectors V. That is, we are able to write it as a lambda into identity matrix times V equal to A into V. So that is a eigenvalue equation. Let P be an arbitrary non-singular matrix. We multiply it with the both sides. Okay, so this can be flipped. This is a simple number, so it identity matrix with P gives you P only, and then vector V remains same. On this side, we have multiplied P into A from the left side. You see, matrix multiplication do not commute, so we have to keep their sides preserved. So once we have done that, we play a simple trick. We introduce a combination of P inverse P in between. So because P inverse P is equal to identity matrix, we can always put them as many P inverse P. This is like fishing a negative fish from the sea or river. So what we have is simply pull it inverse and product. This is a common trick used in the mathematics. Now let's call U a new vector as a P dot V, the product between P and V, and then we get the equation lambda times U is equal to P inverse U. So this says that now we have a new matrix P inverse which has a same eigen value lambda with the eigenvector U, which is defined by this. So this kind of a change or transformation is called the similarity transformation. It is extremely useful, used in many places in the physics and mathematics. So we will have a more look at this as we go along. It looks like that our course in vector space is getting little dragged, maybe for a couple of more days of lectures. Let me stop here and continue in the next video.